Nikhil. Dr. Nikhil Kumar is an accomplished engineering specialist with extensive experience in advanced welding technologies and high-performance battery manufacturing. With a proven track record across leading organizations such as Tata Agratas, Jaguar Land Rover, and WMG University of Warwick. He excels in process development, equipment implementation, and delivering robust manufacturing solutions. His work spans laser welding, battery module assembly, and large-scale process optimization, supported by strong research contributions and industry recognition. Uh, Sir, please. Sir, I am Dr. 𝗕𝗫𝗙𝗪𝗂𝗃, as you know, and Dr. 𝗕𝗫𝗄𝗎𝗃, who is our coordinator, is present with us. Sir, please, the screen is yours.
Hi, good evening, everyone, and good evening, all coordinators and madam.
Thank you.
Yeah, so thank you for short introduction. I'm sharing my screen. I hope my screen is visible.
Yes, sir. Visible, sir.
Yeah, so is it moving forward?
Yes, sir.
Okay. And thank you for giving me this opportunity to present my previous work. And I have been working in this field from last 13 to 14 years. And basically, I have completed my PhD in this laser welding technology. So I'm really enjoyed working in this field. So whatever question arises about welding or laser welding, please stop me anytime. I will be happy to answer. Okay, so my topic is I will be going to cover the various welding processes used in the battery pack welding. So whether it's a module or pack, so I will be cover both. Yeah, so the basic content of this presentation is going to a little background, and I will be covering 3 different welding processes in detail: laser welding, wire bonding, resistance spot welding. But I'm going to show you 2 more processes, which is micro-TIG welding process and ultrasonic welding process in a small. So I'm going to cover this main part in the electric vehicle, which is covering 30% of the costing for the electric vehicle. So I'm going to capture this, basically this battery pack, how this battery pack is made and how they are welded, and why this is very important to have a good quality weld for this battery pack, and why this is very demanding in the current scenario. Everyone is chasing this sector. Yeah, so this is little bit forecast I have borrowed from the survey done in Europe. So this is the left one is the geographical demand of expected to grow by 33% in near future. So the demand of lithium-ion cell is going to grow very fast in near future, which is about 33% annually by 2030. So this is left side is geographical demand. So the China is, like population-wise also China is very high, but also they are in very huge demand of the lithium-ion cell. And the right side is about the which sector the industry is demand. So the mobility sector is going to consume about more than 90% of this whole lithium-ion cell. So this is very important. That's why we are going to cover this battery pack production and how welding is important and how what is a crucial, why welding is very crucial in the welding battery pack. So so this slide is showing the 3 different cell formats. I think most of the people are aware about the cylindrical cell. So this is the very first one is called the cylindrical cell. I think you must have seen in the remote or any kind of toys. This is normally used as a cylindrical cell, and this is pulse cell, and the last one is the prismatic cell. So depending on the vehicle size and the weight of the vehicle and the space requirement and the size available in the vehicle, so the cells were selected. So whether it is cylindrical cell or pulse cell or prismatic cell also. So but the formation of these all 3 cells are same. So each cells has the anode, cathode, and separator, and electrolyte slurry, and positive and negative terminals, and charging, discharging. The mechanism is same. Only the difference is the density wise. And the external shape and the format, like this is the hard casing of material, the aluminum can for this one, and this is the soft aluminum plastic bag kind of materials, and this is aluminum as a nickel plated steel. So, and if you are using this one, then you can see this is the space utilization is very good if you are selecting the prismatic cell, but the space utilization is very less in case of cylindrical cell. So depending on the requirement and depending on the power required and depending on the what kind of vehicle you want to drive using this cell, so they are utilizing by the industry. So the bottom picture is showing the stepwise making battery pack. So this is the left picture is called the individual cell, and the next picture is the module. This is connecting the cells in series, or no, this is connected cells in parallel. So this is called the module. And once these modules are connected itself together, then this is called the pack. So the pack size could be vary depending on the requirement, whether it's truck, buses, or the scooty, or two-wheeler or three-wheeler. So the size depend on the what is the power, voltage, or current requirement for the your vehicle or for your industry. And this is showing the weld, where the welds are important. So for connecting these two cells, because this is showing connection in the parallel. So this black dot is showing the joints. This is called the weld. So it could be any weld process. So, and the strip, this is interconnects. This is made of, this is also called the lattice. Sometimes it's called tab, sometimes it's called the busbar. So three different wording I will be using in the next slide. So this is either lattice, busbar, or tab. So you can see either of these for connecting these two. This should be very conducting material. It could be aluminum, copper, nickel plated copper, or solid nickel. So yeah, so welding. So welding fundamentals. So welding is a process of joining two different materials, similar or dissimilar material, by application of heat or without application of heat. So, and welding, as I mentioned, the welding is a permanent joint. So basically I would say the welding is a permanent joint. So materials would fail, the weld should not fail, like interfacial failure. So materials should always break close to the weld. It should not as an interfacial failure. And to make any large integration or large device or large layout, you always need a welding. So that's why welding is very crucial. It is everywhere, not only in the automobile. It is also in the aircraft, railways, boiler, and ship. Wherever you are seeing, welding is always required everywhere. So I have summarized 5 different processes here in one slide. So these are mostly using in the electric vehicle for connecting the batteries as well as some structural part as well. So the first one is the laser welding process, and the next one is the resistance spot welding process, wire bonding, ultrasonic welding, and micro-TIG welding process. As I mentioned, these are mostly using in the automobile industry for connecting the cell as well as some structural part as well. So I will be showing some example of connecting the cell as well as some structural part using different welding processes. So the principle is very simple. So this is a laser welding process. Here the light is working as a main energy source, the laser beam. So laser beam could be single mode laser, dual beam laser, blue laser, green laser. They comes in different modes or different wavelengths. So mostly we are using the fiber laser in industry for connecting because the beam quality of fiber laser is very good and that is easily coupled with the metals. So for plastic, people are using the diode laser because diode laser is mostly compatible with the plastic. So depending on the material type, the laser is selected. So the basic principle is the melt the material together and fuse them and melt them together to make a permanent joint. So this is basically a fusion welding process. And the bottom left is the resistance spot welding process. Here the energy is coming from the resistance energy. So the resistance between two surface, between two sheet is acting as a resistance energy. If you consider the Joule's law of heating, so H is equal to I square RT. So where R is the current passing from this two electrode, and R is the resistance between two sheet because there must be some air gap between these two sheet. So that air gap is creating the heat itself, that is I square RT, and that heat is quite enough to melt these two material. the faying surface. The joining is basically between these two surfaces, which is called the faying surface, and that is fused together and melt each other. And this is wire bonding. So first, for this wire bonding process, energy is transferred in form of the ultrasonic vibration energy. So basically, we are using here 60 to 80 kilohertz vibrational frequency ultrasound to transfer the energy to this wire, because basically this wire is using to connect. The one end of the wire is connect to the one cell, and other end of the wire is connect to the other cell or the bus bar. So wire is acting as a medium to connecting the two cell, and the wire is connected using the ultrasonic energy, and that energy is very low because the wire itself is very thin, about 50 micron, because this is basically using in the electronics industry. If you're seeing the thin PCBs connections, PCB are connected using the thin cables or thin wires. So this welding process is normally used. This is called the bonding because this is solid state welding process. So this wire could be made of aluminum, copper, or gold itself as well. People are also using gold, aluminum, and copper as a wire material. And the top right corner is the ultrasonic welding, but this is just a bigger version of this process, the ultrasonic welding process. Here also the energy is ultrasonic energy, but here the material thickness is about 0.1 millimeter, 0.2 millimeter, 0.3 millimeter. Here also the same principle. If you see the teeth, so this is gripping these two materials very tightly held, and this material itself is vibrating. The top sheet is vibrating and creating a frictional energy between these two sheets, and they fuse together. So basically here also the vibration energy is acting as a source of energy to melt these two material. And the last one is the micro-TIG welding process. So this is the precise version of the TIG welding process. If you have used the TIG welding process, the tungsten inert gas, the arc is created between the non-consumable electrode and the workpiece, and that arc is sufficient enough to melt the tap, and that tap is melt together the shell material as well. So here I have shown the 5 different welding process, but the only difference is what kind of energy is used to melt the material. Yeah, so I'm going to proceed with the laser welding process. So as I mentioned, to make a modular pack, you need to connect the individual cell together to make a module for a required energy or required voltage or current, because one cell is not sufficient to drive your vehicle or any two-wheelers or three-wheelers. You need to connect the 5,000 cell or 6,000 cell together to get a sufficient power or sufficient voltage to drive your vehicle. So that's why the welding comes in the market, and the role plays very crucial in the battery pack. So you may have a 7,000 or 8,000 weld for connecting the battery modules or battery pack. So here this red dot showing the laser weld. So these cells are connected in the parallel. So these all positive terminals are connected to the bus bar. So we have now connected all this positive terminal to the one of the sheet on one of the bus bar. Now this bus bar is going to connect to the one main bus bar, and we are going to accumulate all this power of this all amp hour. Suppose this is 3 amp hour. 3 amp hour is going to accumulate in all. By adding this all, you are going to have a high amp hour capacity of this itself. So this is example of the power cell. So here this is one of the connection I'm showing here. This is connecting the tap to the bus bar. So this red line is showing a laser weld, and the other end you can also connect one more cell. So like this, you can make a parallel to parallel connection. If you are going to connect aluminum itself on that side, or you are going to connect the copper, then that would be a series connection. So like this, laser is playing a role, or welding is playing a role to make a bigger and bigger pack or bigger capacities module or pack. Yeah, so I have considered one case study for deciding what kind of lattice or what kind of bus bar or tab is to be selected for your particular equipment or particular module, because people may ask you to connect the aluminum, copper, nickel plated copper, or solid nickel, because these 4 materials are very popular as a TAM material. So definitely at the end of this session, you would be able to decide what tab material is good for your battery pack or battery module. So I'm going to consider these four different material, and logically I'm going to prove which material is good for your battery pack. So for this study, you have to go through the coupon preparation first. The approach is to prepare a coupons made of these four different material. The coupons should be the same size. The size should not be vary from one with other. So you just have to prepare the coupon first, and then you have to select the welding process. As I have already selected the laser welding process for this particular case study, and do the welding trials. And after welding trials, you have to do some characteristics measurement for the welds. You have to go through the joint strength analysis like pull test, build test. And next is the weld cross-section analysis. And final is the joint resistance or temperature analysis. As I have added this one because joint resistance and temperature is very important, because we are making the battery pack. We don't want our energy loss in terms of the heat. If you have a under weld, or if you have a very bad quality weld, then you will be end up losing your energy or battery pack energy in terms of heat instead of transferring it to the vehicle. So this is very important instead of joint strength. And finally, the optimization of the process parameter to achieve the good quality weld. Once you have a parameter optimized, then you can use that for the connecting this cell. Yeah, as I mentioned, I have selected coupon first. I'm not going to weld directly to the cell. First, I am going to do the trial and identify the what is the best tab material for my battery module. Then I am going to use that for the battery module welding. So for that case study, I have selected equal size coupons for the all four different material. So the material made of aluminum, copper, nickel plated copper or nickel. So basically there is a four different material combination to be welded. So one is aluminum to aluminum, the next one is copper to aluminum, third one is nickel plated copper to aluminum, and nickel to aluminum. So I'm going to weld one by one. And with the top one thickness, the top material thickness is always 0.3. Is 0.3, and the bottom one material I'm going to use the 0.3 and 0.4 both one by one. Why 0.4? Because the basically this cylindrical cell positive side thickness or terminal thickness is made of 0.4, and the bottom side thickness is made of 0.3. So you have to optimize the both side 0.4 and 0.3 for connecting the module. So at the after welding, so this is you can consider this schematic as a weld, one of the weld piece. This is a schematic diagram of the one of the weld piece. You can consider the weld is going to be formed like this. You will have a terminal on the bottom side and tab on the top side, and you have a weld with the circle, like same shape of 0.5 millimeter diameter weld seam. And after welding, I am going to capture or measure the shear load, lap shear load, joint resistance temperature, and micro imaging. I would say the weld cross-section analysis, because this is very important to capture the weld depth. If you are going to melt the bottom sheet 100%, you will end up cutting, not welding, and you are going to have electrolyte leaking, because you have to go implement those parameters to the battery, and battery is closed casing. There's electrolyte field of electrolyte, so you don't want to penetrate 100% those cans. So the micro imaging is very important after welding before going to the final weld. And vibration is also important because this pack is going to use on the road. So the chances is like vibration especially in India. So you all know the road quality in India. So the vibration check is very important. So we will have to do the vibration test as well before placing it in the vehicle. Yeah. So this is schematic diagram of the pull test. So weld characterization. So this is pull test. So pull test, we all know aware about the pull test. So this is, I mentioned the Instron, one of the setup. So it could be made of any other company. I've just shown one of the example like Instron. So this is one, you can consider this is the one of the weld piece, and this is pulled in the two ends, and you can capture the welder strength by pulling this specimen from the two end. And how the weld strength is captured? This is captured in the load cell. So this is the load cell. You can use a load cell and capture the resistance. See, this is the specimen, and this is gripped on the bottom. Bottom is stationary, and this one is moving on the top. and it is capturing the strength, or you can say the maximum load is captured using the load cell. By this way, you can capture the strength and you can say the whether it's good or bad weld, depending on the whether it's failing from the tab or it's an interfacial failure. And the second one is the weld cross-section analysis. As I mentioned, you have to capture the weld strength as well. You have to check the whether this is 100% penetrated the bottom sheet or this is partially penetrated. It should not be very low penetration. This can be considered as an underweld because this is not sufficient to give us the sufficient weld quality or weld strength because the weld volume is very low in this case. And this can be considered as a good weld because we have not gone to the more than 50% penetration or 40% penetration, as there is a no thumb rule what should be the penetration. But as soon as you get a good strength, as soon as you are going to material falling from the top surface, then you can consider as a good penetration. And this is definitely not a good example and not a good weld because you are going to use very high energy of the laser to penetrate this bottom sheet. You will end up wasting your laser energy instead of using this as a good weld. And the final is the weld resistance and temperature measurement. I have not shown the schematic here. I will show you the proper example of this schematic and the actual setup. So this is pull test, this is weld cross section, and final is the resistance and temperature test. This, if you able to cover this all, then you can tell us the what is the best type material out of this four. So I'm going to cover this all four or the four different welding combinations. So this is a welding setup used for the welding. So you can see in the right corner, this is welding done. So this is a welding head. You can see the welding gun. So this is fixture for gripping two samples together, and the arrangement is made. And this is CNC program G code I have made and welded the specimen. Yeah. So I have shown here the maximum power. So this is IPG laser. This is 150-watt QCW laser, IPG Photonics company made. And this is maximum power of this laser is 150 watt. And the spot size is 28 micron. Spot size, whoever aware with the laser, they easily identify this one is the spot diameter of at focus. At focus, the spot diameter is 28 micron and the wobble mode is clockwise. So I have used the wobble mode or beam oscillation mode for welding these two pieces because they are conducting material. So the laser is not moving in the straight line. They are moving in the spiral this way. This is called the beam oscillation. So that's why there is two additional parameter added here. So the process parameter, you can see the process parameters for this particular laser. So one is the laser power, one is welding speed, and third one is the wobble frequency and wobble amplitude. So this this is called the wobble amplitude as the laser is rotating and moving forward. So this distance is called the wobble amplitude, and this frequency, the more the overlapping, there is a more frequency, and there is a less overlapping means the less frequency. So based on some initial trial, I have randomized the welding power. So I have only changed the welding power, I fixed the other parameter because if I go and change the everything, then I will end up doing the 1,000 trials or 1 lakh trials. So I have done some initial trial first, and I identified the which parameter is more significant and which is not significant. So I have fixed those parameter which is not significant. I have only varied those parameter which is highly significant and which had the most significant effect. So that's why I fixed the welding speed and wobble frequency at some certain value. This paper is already published in the public domain. So this is laser power fixed at welding speed and wobble frequency and wobble amplitude. And laser power is varied. So this is showing the laser power for the aluminum to aluminum combination. Aluminum is the bottom sheet and aluminum is the top sheet. So power is varying from 27 to the 54 in the discrete manner, 27, 30, 36, 42, 48, and 54. Similar for the copper to aluminum, nickel plated copper to aluminum, and solid nickel to aluminum. Yeah, so this is one of the example. I'm showing the aluminum to aluminum weld joint. As I mentioned, I have measured the weld strength, lab shear strength. So what I have seen here in the top picture. So this is showing the weld seam on the top view of the weld seam, and this is the bottom face of the bottom sheet. So this is bottom face of the bottom sheet, and this is the top surface of the top sheet. So from this way, you can identify the which surface is the 100% penetrated. So from the left, right, left, you can see this one is the 100% penetrated, the bottom sheet. So this is not actually this is not you cannot implement this parameter for your battery because this is going to cut the your can, or you can say the end of cutting might be cutting, not the welding. So this can be causing the potential electrolyte leakage from the cell if you go and do this kind of welding. So this is very important to capture the bottom face of the bottom sheet, so which is not visible in the actual cell. So this trial should be done on the coupon level first before go and implement. That's why I've done this trial. Yeah. So what happening here? So this is 27-watt laser power. This you can see this is a no bottom face penetration on this 27-watt, but the weld strength is very low. And you can correlate this with this picture on the bottom left. This is interfacial failure. This is the two materials separated after the full test. This is lab shear test. So this is not an example of good weld. According to definition, the weld material should fail. The weld should not fail. So here the weld is failing. This is not an example of good weld. That's why you are getting very low strength, which is less than 200 Newton. And here the bottom sheet is not penetrating. This could be the very low penetration of the bottom sheet. You will have not sufficient weld volume. And the next one is the 30-watt power. Here you are getting very good strength, which is equivalent to the 500 Newton. And here the sheet is failing. The top sheet is failing. It's broken, and there is no interfacial failure. So you can consider this as a good weld. Why this is considered as a good weld? Because this is fulfilling the welding definition, as well as you don't have any bottom sheet penetration in this one. There is no bottom sheet penetration on this particular parameter. So you have two parameters ready now, 30 and 36 watt. So you can either consider this one as a good weld or this one as a good weld, because both the cases you are not penetrating the bottom sheet, which is good for the battery cell, because this is filled with electrolytes. So you either use this one or this one as a good example, because you are also fulfilling the criteria of the welding. The material are failing. The weld is not failing like this interface. This is considered as an overweld because you are, as soon as you are breaking the samples, but this is over penetrated to the bottom sheet. This is definitely not applicable to our application where you are going to weld the battery cell. So here, what is the maximum strength? The maximum strength you are getting is 500 Newton for the aluminum to aluminum can. And this is the example for the similar example. I have varied the power from the 42 to 78. This is just the top sheet is copper and bottom sheet is same like previous one, 0.3 millimeter aluminum. So here the strength is more because the material itself is strong. The copper itself is very strong as compared to aluminum. That's why we are getting about more than twice strength as compared to the aluminum. So the same kind, by the same way we can pick what is the good weld, because this is the first one is interfacial failure. As soon as there is no bottom sheet penetration, we cannot say this is good weld. This is fulfilling one criteria, no bottom sheet penetration, but this is not fulfilling the other criteria where the material should break. So, but this one, the second one, this is fulfilling the welding definition, and this is also fulfilling the not penetrating the bottom sheet. So the 48-watt power can be considered as a good weld, and that's why you are getting very good strength for this one. And the rest of the parameter can be considered as an overweld because you are penetrating 100% of the bottom sheet. So the laser impression, you can clearly see the laser impression on the bottom face. So they are also penetrating, they are also breaking from the top surface. This is not because of the good weld, this is because of you are cutting or you are creating a notch on the top surface because of the overheat. And this is other tab. This is copper to nickel. This is called the nickel plated copper. The joint name is nickel plated copper. So mostly this is the most popular tab using in the industry because this is to avoid any kind of pits on the bare copper, because bare copper is, you can easily catch pits on the bare copper, discoloration on the bare copper. The people doing the nickel plating on the bare copper to avoid that kind of damages in the oxidation or any bare environment. So here there is a 4 micron or 3 micron nickel coating on the bare copper. And similar concept here used to identify the good weld. The first example is the breaking from the top sheet, and the other example is there is no penetration on the bottom sheet. So here also we are getting very good strength because nickel is making compatible or making help in welding for the laser, because nickel absorbs more energy as compared to the bare copper. So like I would say the reflection of the laser with bare copper is about 90% or 95%, but with this nickel plating, you can reduce the reflection of the laser beam about 10%. Like it is going to be 85% absorption of the laser beam by just nickel coating. And this is solid nickel to the illumin, as I have concluded this one here as a good weld, because I used to increase the laser power, but I didn't able to break this material. But what I found, this is breaking at here at some point, but at that point, sorry, yeah, but at that point I was penetrating the bottom sheet 100%. So I have concluded here as a good weld, because nickel itself a very strong material. So it is not always necessary to break the top sheet, because it could be possible to break it if I could have been made the 2 or 3 circles here, because strength is also depend on the weld area. I think this weld area was not sufficient enough to break the top sheet. If I would have been made the 2 or 3 circles instead of only 1 circle, I would have been broken these samples as well. So I have concluded here because there is no bottom sheet penetration, and this is interfacial failure, but still we have a very high strength. This is about 1000 Newton load. I think this is about 100 kg load can survive with this tiny 0.3 millimeter nickel sheet. Yeah, so why this is important? So next characteristics of the weld is weld cross-section analysis. So based on the previous study, I have selected 3 samples. So which comes under the underweld and good weld and overweld. So, and I have captured, and this is the schematic of how the weld cross-section is done. So you can consider this is the one of the weld piece, and I have done this cutting. This is the cut plane. I have done this cutting using the high precision cutter, and this samples is mounted in the same manner how it is showing, and mounted in the same manner, and then they have polished cloth polish and paper polish, and they have captured the weld bit under the optical microscope. And this kind of image is captured after doing the optical microscope. So this is an example of underweld, because you are not getting sufficient penetration. This is just touching the laser beam to the bottom sheet. So this hardly penetrated the bottom sheet, but this is an example of good weld. And this is an example of the overweld. Why this is overweld? Because you are penetrating the bottom sheet by 100%. So this is definitely not good, because after some cycle, or you may have seen after few cycles, there is electrolyte leaking, because there must be a micro pores to flow the electrolyte from this channel to the outside. So this is not recommended for our surface or purpose in a battery. Not only electrolyte leaking, this is also transferring heat to the inside the cell, that can causing the potential aging for the cell. So this is example of the aluminum to illumin. This is example for the underweld, good weld, and overweld. You can easily identify which is under, because this is not sufficient penetration. This is good weld and this is overweld. So, and this is example for the copper to illumin. So this is also, you can see this is hardly any penetration on the bottom sheet. This can be considered as underweld. This is good weld and this is overweld, because we have fully penetrated the bottom sheet. So this is like identification for you. How would you identify which is good, bad, and overweld? And this is also reflecting in the joint strength as well. For this particular combination, you have seen very low strength, because this one was showing us the about 200 Newton load, and this one was showing about 500 Newton load. And this one was showing also very low strength. I think it was about 200 to 300 Newton load, and this was showing 700 to 800 Newton load. You can significantly see the change in the strength based on this penetration depth and weld width. And this is the combination for the nickel plated copper to illumin, and this is nickel to illumin. Yeah, so similar, like I mentioned, I have selected two different thickness of bottom sheet because the positive terminal of the cans or cells are made of 0.4 millimeter illumin and negative is made of 0.3 millimeter illumin. So I have already captured 0.3 millimeter and we already have a parameter optimized for the 0.3 millimeter. So if anyone want to do more precise optimization, they can do with the full DOE, like response surface methodology, 𝗕𝗏𝗃𝗃 DGNF experiment or full factorial based on this initial trial. So, but I haven't gone through those level. Yeah, so as I mentioned, point three, similar task or similar examination have been done for the point four as a bottom sheet, and top sheet is same here, same dimension, everything same laser. So only there is change in power because the bottom sheet is 0.4 millimeter. So there is a slight increase in the laser power because the bottom sheet is capturing more heat and dissipating more heat as there is a quite thick. Yeah, so here what I have seen here, the same concept to capture the good weld and overweld. Here you can see there is hardly any penetration on the bottom sheet. There is no penetration, seems quite good, seems quality, and we are breaking the top surface from here. So this is fulfilling the welding definition. And this is also fulfilling the battery criteria, bottom sheet not penetrated. So this can be used as a weld parameter for connecting the cell. And this is also a good parameter because here also we are not seeing any penetration. This is also good parameter. This is overweld. This last two pictures. So, so this is for 0.3 to 0.4 and this is 0.3 to 0.4 copper. So same concept here for optimizing. This is for nickel plated copper. This is for nickel. And this is, as I mentioned, this is very important. Let's see this one. So how I measure the resistance and temperature, as I mentioned, the resistance is a very important parameter. If you have an underweld, then this is going to dissipate your heat and you are not going to get that capacity. So your vehicle is going to discharge very early and very soon. So it's better to have a good weld so that there is a very less heat dissipation from your joints because the current will be transferring from the tap to the cap to the cell during the charging and discharging as well. So that this is the main connection point from the cell to the tap or cell to the vehicle engine. Yeah. So how I have captured the resistance. So you can consider this one as a welded piece. So this is tab. The light green color is a tab, and this is the bus bar. The gray color is the tab or bus bar. So you can consider this is a one welded piece, and this is the weld. So to capture the resistance, so to capture the resistance, what I have done, I have passed the current from here and current will leaving from here. So the positive terminal of the power source, which is a constant current power source, is connected here, and negative terminal is connected here. So the current is flowing from the here to here, and we are capturing the. We have made some arrangement or some probe. That probe is connecting to the close to the weld on this tab, and other probe is connecting to the bottom face of the bottom sheet. And that probe are very close to the welds, so that we can capture the voltage drop across the weld only. So suppose we are passing the current as a X amp and the voltage drop is about V volt. So the resistance would be V divided by X because we are capturing the voltage across the weld. So that resistance would be the weld resistance because you are not capturing resistance from end to end. So this is and the same time I am capturing using the thermal camera. And the thermal camera is focusing on the weld area only, and that is capturing the temperature range at the weld because this is current going to pass continuously. So I'm going to pass this current for the 3 minutes or 5 minutes and capturing the resistance at the same time and capturing the temperature at the same time, the real-time temperature and real-time resistance. So this is the arrangement. So this is thermal camera. As I mentioned, this is I'm using the multimeter, not multimeter. This is a picologger. So the picologger arrangement. So there we can capture the voltage drop across the weld. There is a 2-pin that is showing underneath of this sample. So there is a 2-pin capturing the voltage drop across the weld, and that is capturing on this picologger, and we are capturing the temperature. This thermal camera is focusing on the weld area, especially to capture the temperature range, real-time temperature. Yeah, so this is after doing that trial. So I have used 4 different tabs one by one. So the first tab is like aluminum to aluminum. Second tab is nickel plated copper to aluminum. As I mentioned, four different tabs. And this is one constant current is passed for 50 amps current for 3 minutes. So this is captured for 180 seconds. For 3 minutes, I have passed the current of 50 amps and captured the resistance. This is a constant passing current. So as you have seen, there is a spike of resistance, but after a certain period of time, there is a constant resistance. There is not that much spike in the current, spike in the resistance, because after some time, the heat dissipation and heat generation is nearly same. That's after some time. At that period, the resistance is coming about not spike or not that much difference in resistance over the time. So after doing this exercise, what I identified as a resistance, the minimum resistance is captured for the nickel plated copper to the tab welding and maximum for the solid nickel, because this is not due to the welding. This is because of the material itself property, because as you know, nickel is not really electrically conducting material. It's very low electrically conducting material as compared to the copper and the aluminum or nickel plated copper. So from this slide, the takeaway is the lowest resistance obtained for the nickel plated copper to tab welding and maximum for the nickel to tab welding. And this is the piece of metal used for the resistance testing, the top right corner, you can see. So they were equal dimension for the OR4 combination. And this is for the 0.4 as a bottom seat, and this is 0.3 as a bottom seat. The only difference in two is the bottom seat is 0.4 for this combination, and this is bottom seat is 0.3 for this combination. So as the resistance for this one is low, because the current capacity is more for the thicker material, because this is thicker material 0.4. So that's why you are getting low resistance for this material. And this is joint temperature. As I mentioned, I am capturing the temperature at same time while passing the current. So the resistance is measuring by two probe by measuring the voltage drop, and this is temperature is capturing by the IR camera. So I am focusing the IR camera around the weld, just top of the weld, and capturing the temperature raise, because as according to the Joule's law of heating, as you are passing the current, I square RT. So as you are increasing time, you are increasing the heat generation as well, and that is forming the increasing the temperature on the sheet, and that is capturing in the IR using IR camera. So the similar trend is obtained here as well, like resistance. You have a lowest temperature raise for the nickel plated copper and maximum for the nickel, because this is just a reflection of the resistance. The more the resistance, more the temperature raised. So that's why you have got the same trend here as a temperature as well. So why this data is important? Because if you are going to select some tab, so you won't select this one as a nickel, because if you're going to use the 50 amps current with this nickel tab, then you are going to have a very high temperature raise. Then your cell is not going to survive that 60 amp temperature, 60 degrees C temperature. So you have to select either nickel plated copper or nickel. That's why this data is very important. So for 50 amps current, you have to use either nickel plated copper or copper as a material for the tab. Finally, I have summarized this all three characteristics, which is a lap shear load, resistance, and temperature. So as I mentioned at the end of the slide, you will see what are the tabs and which tab is important. If somebody asks me, I don't worry about the resistance and temperature. I just need the strength only. So they can go with this case 2. So case 2 is so if they need the strength only, they won't worry about the resistance and temperature, they can select the nickel, because nickel is the highest strength. So they can select nickel as a tab material. But if somebody is really worrying about the resistance and temperature, and they are giving the first priority to the nickel resistance and temperature, then they select the nickel plated copper, because this is showing the lowest resistance and lowest temperature raise. So as they are all really worrying about the temperature raise or human safety, so they can select the nickel plated copper. But even in the real life, you can see the nickel is mostly using by the industry or the battery tab, because they are easily weldable, and you can use any layman or any kind of non-skilled person can also weld that nickel, because that is using the hand operated distance spot welding process can be used to weld those easily. And also the cost is interesting. The cost of nickel is very high, but still they are majorly using in the battery pack as a TAM material for the cylindrical cell, especially not for the prismatic cell, because prismatic cell I have seen mostly using the aluminum as a busbar material. But the cost is very high for the nickel. So you can consider this all four scenario: cost, the strength, resistance, and temperature for deciding the which tab is important and which tab is helpful or which tab is fulfilling your battery pack requirement. So I have already captured this side where I have captured the lattice to the cell connection. So, but I have also done a study on the lattice to the bus bar connection. So bus bar could be made of aluminum or copper. It could be 1.5 millimeter. I have given here 1.5 millimeter study. It could be 2 millimeter, 3 millimeter, 4 millimeter, 5 millimeter. Again, it depends on the whether you will be using for the heavy trucks, buses, or you're using for the small vehicle. So this bus bar size or thickness depend on the what kind of application you will be using for, because with increasing the thickness, current capacity is also increases proportionally. So this graph or this slide is showing the same kind of concept. The first graph is showing the strength, second is resistance, and third is temperature. So if somebody want to decide so which bus bar and which tab is good for their application, so they can simply jump to this slide and they identify. Actually, this is already published paper in public domain. So this is a slide from that one. So this is aluminum. So you can say the aluminum having the lowest resistance. If somebody want lowest strength. If somebody want nobody want lowest strength, but if somebody want to know what is the strength for the aluminum for particular weld area, because this is welded like same weld area like 5 millimeter circle diameter, they can easily understand this is the strength can be achieved, minimum strength can be achieved by using this aluminum to copper or aluminum to aluminum combination of welding. So from this bar chart, you can say the maximum strength achieved for the tap to the copper busbar means nickel tap to the copper busbar, because nickel and copper is highly compatible material. There is no intermetallic formation between the nickel and the copper, what I have seen. So they are following the all four metallurgical rules. So, and here in this middle one, this is resistance comparison. So what I have seen, the lowest resistance achieved for the nickel plated copper and maximum resistance for the nickel. And similar for the temperature, as the resistance is lowest for the nickel plated copper, the similar for this one, the temperature, the lowest temperature is for the nickel plated copper. So I think this is showing the similar trend like the previous slide, what I have shown here for the tap to the illumine. I think similar trend obtained here as well, but only difference is here I have used a different busbar material, aluminum and copper. So I think this is very useful slide. If you have doing any DOA study or doing some comparison, so you will have to consider these three characteristics, strength, resistance, and temperature for deciding which is the best tab material. As I mentioned here, nobody want their battery cell temperature goes about 150 degrees C. So they won't use this material as a tab material. I think for this purpose, I have used 150 amps current. This is another example. I had one small project with SME. They wanted me to weld this funny bus bar. This is funny bus bar, one of the bus bar like 0.9 millimeter nickel plated aluminum bus bar connecting to the cell. This is 21700 cell, moly cell or 21700 cell. So they wanted me to connect this bus bar to the cell. So as I mentioned, don't try to do welding immediately once you receive the material. You have to do some coupon-based trial first. So the same thing I have done. First, I have done coupon trial without doing any final trial on this actual bus bar, because there might be thermal runaway, chances of runaway if you don't have any idea about what power is required to connect this. So I have done that exercise, what I have shown in the previous slide. I have done some coupon trial first. So this is, I have prepared a coupon of the material made of this, whatever material used for making this bus bar. I have used this material for making the coupon first. And the material used for making this can, the same material used for the coupon as a bottom sheet, and this is the top sheet. And This is the trial I have done. This is fixed studying for connecting, for holding these two materials. And this is the same exercise like this is pull test, what I have shown in the instone used for the pull test. And this is resistance measurement. So you also have to capture the resistance before giving handover to the client or customer, like what is the resistance carrying capacity or current carrying capacity with with this weld area, how much resistance or how much current can be carrying by this weld area without doing any thermal runaway. So that's why this is also important to capture. And this is what I have mentioned, the weld cross-section analysis. So this is, you have to check the whether you are penetrating 100% the bottom sheet. And this hardness analysis, this is additional test I have done here, hardness, because this is two dissimilar material. This is aluminum, nickel plated aluminum to the steel can. Two different grade of material with different thermal property and different electrical property. And finally, I welded successfully by following those steps, doing the coupon-based trial and doing the resistance, temperature, lab shear test, and optimize the parameters successfully. And I have welded this material successfully, the bus bar to the can material. So initially the trial is done on the can. And once I satisfied there is no bottom sheet penetration, then I implemented this parameter to the actual bus bar to the cell material, actual cell. And these are the tests I have done for the cans. Then I have seen there is no bottom sheet penetration, but there is a cracks because of this is two dissimilar grade of material. This is aluminum and the steel. And this is the lab shear test for three different repetition. This is current carrying capacity. I have shown how much current can be passed. Like if you go for a 90 amps, then there is a very high temperature raise. So it is suitable for 45 amps current maximum, because current company are asking for the 15C or 10C current. So that's why I have done this testing, like about 45 amps current to check the 10C of this cell. Yeah, so till here I have done the cell welding, and this is another example of the structural welding. As I mentioned, I will be showing some structural joint, because this is also using for the cell cooling. So this is cooling channel. This is normally used for the cooling the cell. So this is another interesting project where I have to weld this module manifold to the cooling channel, and the spigot. This is spigot. So welding this is spigot as well as the cooling channel to the module manifold and the top surface on top cap. So this is a schematic diagram of the aim is to weld this cooling channel to the module manifold. So this is the red line is showing the weld interface schematically. So before doing this trial, again, I have done some coupon-based trial before doing this one. So this is coupon-based trial. I have identified the which kind of this joint is. This is fillet edge joint. After placing this on this module manifold. So this is fillet edge joint. I have done some initial trial, which is some coupon-based trial. And once I have satisfied with the parameter, like there is no bottom sheet penetration and having a low pores, or there is no pores, no cracks, then I have implemented those parameters to connecting the cooling channel to the module manifold. So this is welding. Yeah, this is successfully welded. This is the final product after doing welding. So this is cooling channel to the module manifold welding, and this is spigot. This is used for the flowing the cooling liquid, and this is final top cover welding. So basic idea is to do the coupon trial first, and once you are satisfied with the parameter, then do the final component welding. So the same technique or same principle has been used, or same approach. So this is done by myself only. Yeah, so this is basically I have used this and the top cover to the module manifold and module manifold to the cooling channel welding. And this is the final product. And this is another example of the power cell welding for connecting two power cells. And this is example of the prismatic cell welding. So this is a sport cell or 86 volt and 86 amp hour cell. This is also in public domain. I have a published paper in this one. So this is a negative terminal. This is positive terminal. The bus bar is connecting using the laser welding process, because this is a very thick material. I think no other welding process is enough to weld these materials apart from laser welding process. So for this process, I have used dual beam welding process. So laser comes on different welding process, as I mentioned, single, dual, green, blue laser. So I've used dual beam welding process for this purpose. Yeah, this is another welding process. This is wire bonding. So as I mentioned, the vibration energy is used as a for the welding this wire to the substrate. So this is, as I mentioned, this is the connecting wire, and joining this wire, we have used the vibrational energy. This is the ultrasound energy or ultrasound frequency is about 60 to 80 kilohertz. So there is very small amplitude. So because this is a very soft material, this is 100% or 99.99% pure aluminum wire. This is very soft aluminum wire. So we have only used very small amplitude of the ultrasound. So as this is a wire guide, so wire is fitting from this wire guider, and this is cutting blade. So after welding, this is cutter is used for the cutting the wires. There's a bonding tool that is made of tungsten or any hard material to pass the energy to the substrate or energy to the wire and transfer it to the substrate. So this is example of connecting the two materials. So see, yeah, so this is another welding process, resistance spot welding process. So there are two arrangement is possible in resistance spot welding process. So this is not possible. This is called the parallel arrangement. So one of the electrode is coming from the top and other is coming from the bottom. So as we don't have access to do the welding from the inside of this can, because there is no through hole from the bottom. So this arrangement is normally used for the connecting the cell in the industry. So this is called the series arrangement of the electrodes. So current is passing from this positive side and leaving from the negative side, and the resistance between these two sheets act as a resistance energy, and that is melting these two surface and creating a nuggets. So this nugget size is the weld strength is depend on this nugget size. So higher the current is larger the nugget size, and lower the current is smaller the nugget size. And the resistance is also varying depending on the nugget size as well. And this is the various, this is 21700 cell, and this is the 18650 cell. And this short indication or short notation is showing the process parameters applicable for the resistance spot welding process. So WC is the welding current and WT is the welding time. Similarly, this is a hold time, squeeze time. This is preheat current. It can be done in the preheat and the main current. So it has, I have done first preheat current, lower preheat current, and then I have done welding. So it can be arranged in the different manner as well. You can also do the preheat more and the low welding current. So it is up to you what kind of material you are using, whether you want to break the oxide layer first and then you do the welding. So that kind of concept is used here. Yeah, thank you.
Hello.
Hello.
Yes, sir. Thank you, sir. Is there any question? Please, participant. Anyone want to ask any questions? Hello.
Hello.
Anyone want to any question?
I think everyone understand everything.
Yes, sir. It is given future scope. Thanks, sir. So most of the participants are putting their views on the chat, sir. So thank you very much, sir. You have given time from your busy schedule, and we have considered our requests also. Thank you.
It's my pleasure. Yeah.
Thank you very much from our organizing team, on behalf of organizing team, as well as 𝗕𝗏𝗃 faculty members, sir. Thank you, sir. Thank you very
Thank you.
much. Thank you
Thanks a
very
lot for giving me opportunity. Thank you.
much, sir. Okay. Now participant can leave. Today's session over. You can give your attendance the given link. Tomorrow we'll start the program at same sharp 6 p.m.